Okay, so why two-mode networks? From my point of view, I think two-mode networks are extremely important for network analysis because most social systems, and if not all of them, can be better modeled if bipartite graphs or two-mode networks. I really like this quote by sociologist Bart van Heijden that says, "Human beings are social through and through. They cannot survive in isolation. They can only live in groups, in hordes, in tribes, in collectivities." With that said, we can actually boldly claim that all social systems have a latent bipartite structure. And I advocate this reasoning on this preprint, Mechanisms and Emergent Properties of Social Structure, which is actually an ongoing work, where I bring concepts from sociologists Scott Feld and Ronald Brigger to explain how two-mode networks can facilitate our understanding of mechanisms of network formation and the structure of social systems in general. The underlying idea is that we always belong to or participate in some sort of collectivity, like families, clubs, workplaces, religion, schools and universities, political parties, and so on. So, for any activity that we do in our daily lives that involves someone else than just oneself, of course, we can associate some collectivity to individuals or individuals to collectivities that we will call here circles. So I'll just refer to collectivity as circles. And we can use them even when the collectivity or the circle is made of only two people, like a couple of kids, for instance. Well, with a couple with no kids, for instance. So this is part of the beauty of using two-mode networks that I think. They generalize all our interactions, including pairwise ones only between two actors. Apart from that, we can still use one-mode networks that are the projections of the original two-mode network. That is, we have more information overall about the system that we want to study. So usually we are more interested in the set of nodes that have agency, so we create those projections. And in those projections we connect actors if they participate in the same circle. So then we have the two-mode networks and the projection to analyze. But a point to note here that's important is that because social systems are mostly made of this bipartite structure, the one-mode projections usually have different structural characteristics than those one-mode networks in biological or artificial systems, for example. For instance, we have social systems that normally present higher clustering, that is the formation of triangles, or the idea that the friend of a friend is also my friend, and higher degree associativity, that is that popular people tend to connect to popular people and unpopular to unpopular. So those characteristics are more in evidence in social systems than in others. Okay, so let's move on to some mathematics and notations. And I don't want to go in details here, but I think we should cover at least something that will be helpful when we are talking about graph objects in Python and loading data using adjacency matrix, for example. So a two-mode network is a bipartite graph B that consists of three sets of things, two sets of nodes and one set of links connecting them, those nodes. Okay. U is the set of nodes that represent actors, individual people, while V is the set of nodes that represent circles or collectivities that we saw. And E is the set of nodes that represent the links or edges. That's why we use E here for edges. We read this thing here, this mathematical notation, like this. So we have a link between nodes U and V such that node U belongs to the set U and node V belongs to the set capital V, let's say. Okay, and that's all. All right, it's simple like that. Then what I like to do is to use this toy network here to illustrate just what I'm saying. It's a bit old because I think like half of these players are already retired, but it still like shows the idea here, right? And it's what, like the set of nodes U, they are the actors or the football players connected to the circles or football clubs, and we have the set of links E representing those connections that players that have played in those clubs. All right. We can represent networks also in a form of adjacency matrix, okay? But two-mode networks have these particular characteristics that we use what we call a block matrix. And let me try to make it clear. Block matrix because we have blocks of zeros, so we can see all the zeros here. That is, there are no connection between the row-column pair of the nodes. They are in the same set, so you see like the letters are not connected to the letters. And block of the adjacency matrix and its transpose, so the adjacency matrix and its transpose kind of like a mirror, the transpose kind of a mirror, connecting nodes from different sets. So you see like we see the numbers have connections with the letters, or the letters have connection with the numbers, but the letters don't have connection with the letters and the numbers don't have connection with the numbers, right? And here the letters are just the football players and the numbers are the clubs. And what I was saying, I just think that it's important to remember is that in a two-mode network, nodes of the same set do not connect to each other, right? So it's like football players do not playing other football players, and clubs do not have other clubs playing for them, this sort of thing, okay? So that's why we do not connect. But for that, we have the projections. A one-mode projection can be a graph G sub U, consisting of a set of nodes U, and a set of links L sub U, while it also can be a graph G sub V with set of nodes V and links L sub V. The G sub V projection is also called out there as a top projection, and circles are also called top nodes. And the set of links L sub V is composed by, so here's this notation here, it's composed by nodes V and V prime, such that these nodes belong to the set V, and there exist links connecting U and V prime in the set of links E of the two-mode networks. That is, nodes are connected in the projection if they share a common neighbor in the two-mode network, and that's all. That's all that this mathematical notation is talking about, okay? And of course, we can do the same for the actors, or the bottom nodes and the bottom projection, okay? That's this notation down here, right? When we talk about adjacency matrix, the top projection is the transpose of the adjacency matrix A times the adjacency matrix itself, while the bottom projection is the adjacency matrix A times its transpose, okay? So that's just the difference between those two equations. And the thing is, this is so because we have the actors as the rows and the circles as the columns of the adjacency matrix, like I show in the previous slide. But okay, if this feels too complicated now, don't worry, because the presentation will be available for you, and then you can of course ask questions later on and so on, okay? But that, I think it's important to have this idea of the adjacency matrix here, right? Okay, but like I said before, we are usually more interested in the bottom projection or the projection of the set of actors who have agency, okay? So then instead of saying G sub U and L sub U, we can just call G and L to make it easier. And the adjacency matrix A sub U, we change to A sub G, so we're talking about the projection G. And A sub G is now a square matrix. That is, it has the same number of rows and columns. They are now the actors. Okay, so we can see the actors associated to the letters here in this illustration. Right? The values we see now in this matrix represent how many circles they are in common between a pair of nodes in the two-mode network. Okay, and the diagonal, the values between the same actor, so A to A, B to B, C to C, and so on, just represent the number of circles that that node participates. Okay, so for instance, node C, Ronaldo played for 3 clubs: Real Madrid, Barcelona, and Corinthians. Okay, but hold this idea for a while, because now we are moving on to the types of projections, and we go back to these numbers in a while, right? So for a bipartite graph, we can have mainly 3 types of projections: simple graph, multigraph, and what we call weighted graphs. And we're going to talk about just the simple weight graph here. Why? Let's start with the simple graph. Simple graph projections. We have only one possible link between pairs of nodes, and links are never weighted, never have some value associated to them. So the links between nodes either exist or they don't. And that's all for the information that we have in the simple graph projection. In a multigraph projection, we can have multiple links between pairs of nodes. So in the toy network here, A and B and C and D participate in 2 circles together, right? And thus they have these 2 links between them, and these links are also without any weight. So the multigraph projection here, we are talking about several possibility of several links between 2 nodes, but with no weights in those links associated to those links. So the adjacency matrix of the projection that we were talking about in the previous slide, and I said hold that thought, is actually the adjacency matrix of the multigraph projection here. Okay, but finally we have a weighted graph where there is just one possible link between a pair of nodes, but those links can have values associated to them. And there are many ways of calculating these values or for those links. And the simplest method is represented, for obvious reasons, for what we call a simple weighted graph. So in the simple weighted graph, the value of the link weight between a pair of nodes is the same as the number of common circles these nodes have in the 2-mode network. That is, the adjacency matrix of the previous slide again is the adjacency matrix of the simple weighted graph. You see, so there are similarities between those 2, between the multigraph and the simple weighted graph. Okay. The multilinks and the weighted links are the result of what we call overlap. Okay, we also call overlap force cycles, and we are not going to explore this in detail today, but these overlaps generate what we call redundancy, right? And this redundancy, like the overlap and of course the redundancy, they are directly related to cohesion and segregation in social systems. But again, that's something for another day. Okay, when we move forward to properties of 2-mode networks and the projections, we have to talk about degree first thing, of course. Okay, degree and degree distributions are going to be the properties on which we will focus here today, right? And the reason for that is because we are talking about 2 sets of nodes and different types of projections. So we will have 4 types of degrees to talk about here. In the 2-mode network, we have the degree D sub V, that is the degree of node V in set V, representing the size of the social circle. That is how many actors participate in that social circle. Second, we have K sub U, that is the degree of node U in set U, representing the social activity of an actor. That is the number of circles in which the actor participates. Okay? And there's an important relation between these 2 that we represent mathematically like this. And this is just saying that the number of links in the 2-mode network, it's equal to the sum of the sizes of all circles in the network, which is in turn equal to the sum of the social activity of all actors of the network. Okay, that's all. For the projections, we have Q sub US equals to Q sub UW. That is, the degree of node U in the simple graph and the simple weighted graph are the same and represent the popularity of an actor. The popularity is what we call the number of unique neighbors of the actor, okay? And then we have the fourth type of degree. Q sub UM is the degree of node U in the multigraph projection and represents the strength of an actor. That is the total number of interactions that that actor has with others in the network. All right. What I find particularly beautiful in these relations is that the popularity or the strength of an actor results from the distribution of the social activity modulated by distribution of circle size and the level of overlapping in the network. And all this information coded in this relatively simple equation. Okay, so I'm trying to make it clear here because those concepts are of course a little bit complicated, but the idea is, okay, the popularity of an actor is the sum over all the social activity, that is the sum of over all the circles of the circle size minus 1, which is the actor herself. Okay, so again, the popularity of an actor is the sum over all circles that this actor participates in, but summing the sizes of those circles. Okay, and this inequality depends on the level of overlapping of that actor. So the strength does not depend on this overlapping. So the strength of the actor is equal this expression here, all right? And this inequality is valid only for the popularity and depends on the level of overlapping in which the actor is involved. Okay, so that's, I think it's really beautiful. It's like all this idea of how people interact with each other concentrate in a simple equation here. Okay, all right, so from that we can say that mechanisms that operate network formation are acting in the structure of the two-mode network, right? Here we have homophily, and homophily of course depends on rich data, and therefore we will not explore today because it becomes more complex. But what the idea here is that when we look at these mechanisms, social activity, overlapping, and homophily related to the composition of the circle and the circle size, so when we project all those, when we see those mechanisms creating the two-mode network, and then we project the network onto the set of actors, and we use this projection to analyze our system, we naturally have the network properties that we observe in empirical data, right? That we are used to seeing in empirical data, which are heterogeneous distribution of popularity and strength. That's we have like few nodes with many connections or interactions, and most of nodes with only a few of those connections interactions. We see high clustering naturally resulted from the projection as well. And more interesting, and of course for another day for discussion, is that we can see the level of cohesion and segregation of communities. Okay, and again, I discuss all these mechanisms and the network structure in this preprint, on which I'm still working to try to put all this piece together. Then, for our practice lectures that we are going to do next, we'll see how to work with degrees and degree distributions, how we can calculate the level of overlapping of the two-mode network, and how to create visualizations for both the two-mode network and the projection network. Some other topics that we will not discuss here because of time, of course, but we can certainly discuss at some point. Again, homophily in the composition of circles, the cohesion and segregation effects due to overlapping, related to community formation as well, really interesting, and clustering measures such as redundancy that we mentioned here, and others such as Six cycle. Okay, so let's have a break now. This is the introduction that I wanted to give, and yes, let's take some questions. Okay, so let's start with the coding part of the workshop. So here I have a blank Jupyter notebook open. I'm just gonna change the name, give it a name like workshop, for example, and we can start coding right away. So first I'm going to import network X, and I'm also going to import from network X algorithms the bipartite algorithms. Okay, so network X doesn't have a specific network class to deal with bipartite graphs or two-mode networks. So we're just going to use the normal simple graph object, and I'm just going to use simple graph object because here our actors are going to be connected to circles or not. So our links are going to be binary, either 1 or 0, they exist or not, right? So here just the simple graph will do for us, and then I'm going to create the bipartite graph, the simple graph object B. So we can just add node normally as we would do for one mode network, but here the trick is that we are going to assign to the nodes every time that we add a node or a bunch of nodes. We're going to assign an attribute that will inform us to which set of node that node belongs. Okay, so here I'm just creating this attribute called bipartite, and I'm assigning it a value 0. So this node 1 has attribute bipartite equals to 0. Okay, and of course we can also have, for example, a list, some kind of list of nodes, 2, 3, 4, and 5, and then we can also add node from list. Okay, and just list 1 here. Oh, but I forgot to give the nodes the important attribute so we can check to which set they belong. Okay, we can also add nodes from a list straight away here. So like for example A, B, C, D, and we can give them the attribute bipartite equals to 1. So the letters will be our actors and the numbers will be our circles. Okay, so if you just print the nodes of B with the data, we're going to see that number nodes have attribute 0, bipartite equals to 0, and letter nodes have attribute bipartite equals to 1. Right? So we can now think of how we can inform network X that we are dealing with a two-mode network. So far network X has no clue that we are doing so, right? So to help us with that, we are going to, after we add all the nodes that we want, we are going to extract the sets of nodes using this attribute. So what we're going to do is, for example, the circles, they're going to be a set of each node for node attribute in bnodes data true. It's important to have data true if the attribute bipartite is the same as 0. Okay, so here we are creating a set of nodes. In the set of nodes, every node will be part of it if if its attribute its bipartite equals to 0. In the other set, actors, we can only do like this. We can take like the set of all nodes of B minus the set that we just created. Okay, so if you print, for example, circles, and then we print actors, we will have that. All right. And now, of course, we want to add edges, and again, we can add edges individually, like for example, just, I don't know, taking a random, something like this, or we can add edges from a list. So what I'm gonna do here is just show you how to create a random edge list. So I'm gonna just create this, like, oh, I'm just gonna randomly choose from the list of circles and randomly choose from the list of actors, and I'm gonna do this, I don't know, like 50 times, for example. Okay, what did I do wrong here? Oops, that's right, for in range 15. There we go, I was missing one here. Okay, so now we need to add those, right? Add edges from our edge list. Okay, and then what we have is all this. All right, so not necessarily you're going to have now 15 plus 1 edge in this network, because this random process sometimes choose the same pair of nodes, and because we're dealing with a simple graph, we cannot have multiple links between nodes. So let's just check how many edges we have in this network. 12. Okay. All right, and then we can just see what we have created here in this bipartite network. Draw network X, B, and there we go. That's what I have. It might be useful to align the circles in the actors in straight lines horizontally or vertically. So we can do something like this, B, and then we can use an algorithm for positioning the nodes. So I'm going to just use like the bipartite layout using B. I'm going to use the circles here as the reference, so if I choose vertically they will be in the left, if I choose horizontally they are going to be on the top. So I'm going to just choose horizontal, and there we have. Okay. All right, so that's good. What we can do is, for example, extract the degrees of those nodes, right? So we call like circles size, and the actors activity, it's equals bipartite. So I'm again using the algorithms for bipartite degrees of B, and then I have to already tell here network X which one of those two we are talking about as actors in circles. So if I give here actors, network X, you understand that the set of nodes that represent actors is this one here. Okay, so we do this, and then if we just print the circle size, circle size. Then we see we have a list of tuples, and then we have node 1 has degree 2 or size 2, node 2 2, and then and so on, right? And if I print the other actors activity, we have the activity of each actor here. Okay, so that's how we can extract the degree, or we can just like do like this. For example, I wanted to be node, let's say node C, and then we have nodes C, and then we have, for example, information, and then we can also just print the degree of node C, and then we have 3, for example. Okay. Then next we can create projections, right? So we saw in the introduction that one of the interesting things about two-mode networks is that we can use their projections as well. So we can create a simple graph projection, just bipartite projected graph, and I have to specify onto which set of nodes I want to create this projection. So here's going to be actors connect to actors. We can create the multigraph by doing using the same actually function, but then I have to specify that I want a multigraph projection, and we can also create a weighted projection, remembering that we are going to create here the simple weight projection. Again, specifying onto which set of nodes we want to create this projection. Okay, and that's it. Now we can just use the same things, for example, to see the degrees of the simple graph projection. Or we can look at all of them. Let's just put here quickly. So the multigraph, the weighted, and the weighted is specifying that I don't want just the degree of the node. I want the weighted degree of the node. So you see, like we saw in the introduction, the simple graph degrees are the same as the weighted graph degrees, and the multigraph degrees are the same as the strength or the weighted degree of the weighted projection. Okay, so this was just to give you like a brief introduction of how we add nodes, add links, and how we do the trick of telling network X that we are dealing with a two-mode network or a bipartite graph object. Okay, now what we're going to do next is I'm going to show you how we can load two-mode network data and create a two-mode network from an edge list or from adjacency matrix. Okay, so let's start with the edge list, and for that I'm going to import pandas. I'm going to use pandas to read the file and to deal with it, the information. And it's important to remember that the file has to be in the same folder as your Jupyter notebook, or you have to specify here the path to the file. But here I have the file in the same folder. I'm just going to do border director.csv. So this dataset is a dataset of individuals, directors that sit on the company's board. Okay, so we have this two-mode network of directors that participate in the board of the companies. Okay, and we load the data, and then that's our data frame. So here it's simple to extract the set of nodes because we already have them in different columns. So if you just read like directors, is going to be the list of the data frame with the column director, as we see here, director. Okay, and actors, or let's call, no, actors, not, sorry, boards, it's going to be the list of the data frame with column board. Okay, the thing is, here these lists are going to have repeated elements because this is an edge list. So we can see here, for example, top 1, top 2, top 1, top 1, top 1, top 1. This is a board named 1 with all these directors named bottom here, right? So if we want to just extract the set, it's easy to do that just by doing like this. In the set of boards. Okay. So now we can, for example, check how many directors and how many boards we have in our data set. Okay, and to create the network, I'm just going to create a function here that we create from edge list. I'm gonna give this function the circles and the actors, and I'm just going to use this general variables top and bottom because I used to do that. Like the circles, I used to call them top nodes, and the actors, I used to call them bottom nodes. So what we're going to do is that, okay, we will have our graph object, and then we're going to iterate through all the rows, because each row of our data frame it's an edge, so I'm going to iterate through all of that. And for do that, we can simply iterate through the size of one of our list of nodes. So I'm just going to give here the top. So this is important. This is not the set, because we're dealing with edge lists. These are not the sets of nodes. These are the lists. These guys here we're gonna use. Okay, so okay, b add node, and then top I, this is gonna be bipartite 0, b add node, oops, sorry, bottom I is gonna be bipartite equals to 1, and then we can add edge top I bottom I, and we return our object. Okay, so if you just call this create from edge list function and give them the list as we extract from the data frame, directors, no, sorry, we have to give the circles first, so boards and directors. Okay, what did I read wrong? Okay, that's length of top. There we go. Okay, so now if you do again like print the length of B nodes, we're gonna have the sum here, 1777. Okay, and we can also check how many edges we have in this network. And as soon as we have the network, we can already do the projections the same way I showed before. and we can start doing an analysis. But I just wanted to show with this data set here how to create a bipartite network using an edge list as an input. Okay, now I'm going to overwrite a data frame, and I'm going to use Adjacency Matrix to create that. And I'm just going to copy the name of the file here. And this is a data set where members of this group, this mafia group, is connected to meetings that they participate, in which they participate. Okay, so that's how our two-mode network here. One set of nodes are the members of the mafia group, and the other set of nodes are is the meetings in which they participate. Okay, so we have our data set, and then let's see how it goes. So there we go. Now the meetings, and here we have the members, the actors. So let's just call this events and actors, and we see most of them are the values are 0. That is like these members did not participate in that event, but we have some here that show when they participate. Okay, all right, so to do that, it's to create a network from this, it's fairly easy as well. First, I'm going to extract the events, and the events is just the header of the data frame, and we can get from this, but I'm going to exclude the first column, because the first column is showing the actors, right? So I'm just gonna grab from here on, and the actors, it's quite easy. It's just like we did before, is the list of the data frame of the column with name actors. Okay, and here we don't have a problem, because as this is a Adjacency Matrix, this list will be already the set. We don't have repetition here, because in Adjacency Matrix we don't have the repetition. Okay, so there we go, there we have. From that, we have just to do another thing, that we need to drop the column, the first column. So I need to identify that I'm gonna drop the first column. That's why I use X as Y1, because we don't want that column with the name of the members. We just want the values 0 or 1. Okay, so we drop that. Oops, what did I do wrong? Column, and again columns. Okay, good. So from this we can create an Adjacency Matrix using NumPy. So I'm just gonna create the Adjacency Matrix using df to NumPy function to NumPy, and I'm gonna put df. Oh no, we already do df. All right. So if I print the Adjacency matrix now, we just have the numbers, and that's what we need to create the. We just have the values, and that's what we need to create the network. So I'm gonna create a function here, call create from Adjacency Matrix. I'm gonna give the now those two are the set of nodes, like I said, because the Adjacency Matrix we don't have a repetition, and the values, the matrix with the values. So again, nx.graph, we add the nodes, add nodes from, now I'm gonna just do the top and give bipartite equals to 0, add nodes from bottom bipartite equals 1. And then what I'm going to do, I'm going to now iterate through each row, range length of bottle, to get each actor, iterate through the events, length top, and if the value of that actor with that event is 1, then we add an edge top j. Well, let's keep the order to make it easier to understand. Top I, bottom I, top j. Okay, and then we are going to return b. And hopefully now if you just create from adjacency matrix and we give first top, and top we gave the name events, then bottom actors with the adjacency matrix. Okay, what did I do wrong? Add nodes from, and something else, bottom, it's not defined. Okay, so here we have a typo, and there we go. Okay, so I'm going to stop this part now that we saw how we can create a two-mode network from scratch and how we can load data, two-mode network data from an edge list or from adjacency matrix, and then we can take some questions now and we come back with doing some analysis. Okay. Okay, so let's continue. And now that we have our two-mode network ready, we can start doing some analysis of it, right? And then we're just going to start with the degrees. So we can capture the degrees of the two-mode network again. So I'm just going to the degree of the circles, events size, and the degree of the actors or the actors activity is the bipartite degrees b, and then I have to specify which set of nodes is the second one here. Okay, that's important to remember. Right, so then we can just check these two degree distributions of circles size and of actors activity. And then we see, okay, we have again tuples, lists of tuples. So like in this event, 13 people participated, in this event 12, and so on. And if you scroll down, we have the members of this mafia group and how many events they participate. All right. So if we do this, if we have the degree, we can have an idea of the degree distribution, so we can see how many events have certain sizes, how many actors have certain activities. So to do that, I am going to import matplotlib so we can plot figures. And to make it easy, I'm gonna just count the number of times each degree appears. So that's how we're gonna get the degree distribution of each set of node, right? We're gonna count how many times each degree appears. So we can do like that. If the event size distribution, sorry, I'm gonna use the, have I imported counter? I don't think so. So let's import just to make sure Now let's import from collections, import counter. So counter is gonna just count, just do what I was saying, just count how many times each degree appears. And I'm going to sort just to make it easier for us. And I'm gonna use the dictionary event size. But then just the values, again, it's just the degrees that the value of the degrees that we are interested in. And the actor activity distribution, again counter, let's sort to make it easier, dictionary actors activity and the values of the degree. Okay, so just to give you an idea what we have created, now we have, for example, we have 73 actors with degree 1, 27 actors with degree 2, 12 actors participating in 3 meetings, and so on, right? Because the degree is activity of the actors. Okay, so now let's plot this degree distribution so we can more easily see, right? To plot this, I'm going to create a function, but I'm just going to copy the whole function because it's too much and we would spend too much time here. But again, this material will be available to you, so you can just check what it is. Okay, I'm just can quickly explain what's going on. So the function and the parameters that we are going to use here, just like defining the environment for plotting the figure. This is doing the plotting itself, and then here is just like tweaking some parameters to try to make a nicer picture. Okay, so we have this thing here, and then if you just call it this function, you should just call this function, and we give the parameters. First the top distribution, and the top distribution is event size distribution, and the second one is the actors activity distribution. Then we're gonna have something like this. Okay, so now we can see how many nodes we have for each degree. So like, for example, meetings of size 6 are the most common, and there are 8 meetings of size 6. Okay, and people that participated in just one meeting is the most common, with about 70 of those people participating in just one meeting. Okay, and then again we can use our projections, right? So I'm just going to copy again the projections where we have it. There we go, here, so we can just go faster because it's the same thing, right? We are using actors as the variable. Yes, okay, so we should do this, and that's it, that's done. But then we have to calculate the popularity distribution. So I'm going to just do similarly as we did before, but now we are going to use the degree of the graphs. So we are going to use the degree of the graph, so we're going to use values, and I'm just going to copy this and do this, and then I have here M, and this strength distribution, right? And we can make another function to plot this two distributions, because this is nice to see them together. So here we have two different figures, right? Two figures in one. And I think when we are looking at popularity and strength, it's nice to see both of them together. So again, I'm just gonna copy the function because it's too long and we would spend too much time, but the idea is the same. But the difference is now we are not having like two subplots, we're just having one. And then if you just call the function plot project distribution, and we're gonna call now it's gonna be this, and is that right? Yeah, first is the popularity and then is the strength distribution, and there we go, we have the degree distributions together. And then we can see that some people have much higher strength than popularity, okay, and those differences are because this difference between those two distributions is because of the overlapping that we're gonna see in a minute. Okay, so we can just like see some numbers like who are the the nodes with top degrees for each of the 4 distributions. So I'm just copy again a function. This function here just will give we will take the distribution and the type of the distribution, and we'll give like the 5 most common, or the the highest, the 5 highest, or let's say the 10 highest degrees. Okay, so then we can just call, like, for example, get highest event size, and we are talking about event size, just so you see like it appears here just to make it nicer, but actually we don't need this if you don't want to, so just to know what we are printing. And then we can get highest actor activity, and then say actor activity. So we see those with highest activities. Then we can get highest popularity. So we have the popularity. No, we don't have that dictionary. You have to use GS degree, and then we can just popularity, and finally we can get highest strength. There we go. Okay, so you see that sometimes there are different in the order of like the highest popularity, highest strength, and this is because how people participate in different meetings with those with other people, which is the overlapping. So talking about overlapping, I'm just gonna copy here a function to count the number of 4 cycles or the level of overlapping. So this is a bunch of mathematics, you can just use that, and then you just can like print 4 cycles of B, and then we know how much overlap. So we have like 1782 4 cycles, so that's the amount of overlapping that we have. Okay, the other way of looking at overlapping is comparing the popularity and the strength of each actor. So again, I'm just gonna put here how we calculate this relationship between popularity and strength, which I call diversity. So it's the diversity of your neighbors in a sense, right? And then we can just like see, for example, some of those, how diverse the neighborhood of Antonio Lamamor was, and so on. Okay, and again we can do some plotting. I'm just gonna copy again, but right away without creating a function. I'm just gonna plot this plotting here is the correlation between the popularity and the strength of each actor. Okay, so we have something like this. So see, like when actors have low strength, they have almost the same value of their strength and popularity. That is, they are not participating in too much meetings with others same, so they don't have much overlapping. But then as people start to participate more, they participate in common meetings with others, and then the strength diverge from this line here. This line would represent when the popularity and the strength is equal. Okay. All right, so I think we should move on now to the last part of the workshop, and that is visualization. Okay. And for the visualization, I am going to just copy again from a previous script that I have, otherwise it would spend too much time. But what I'm doing here is I'm extracting the isolates because there are some actors that did not participate in any meetings. I'm not sure why they kept them here in the data set, but they do not participate, so I don't want to have them. I don't want to have them in the visualization, so I'm just removing them from our two-mode network. Again, I'm just creating the environment for the figure. I'm going to use the spring layout algorithm, like to get the positions of the nodes. I'm going to use colors, red for the circles and blue for the actors, and I'm going to draw them like here. So, like for example, I assign the node colors here and the node size here. I'm just doing some tweaking a little bit so it becomes a nicer figure. Okay, that's still a simple figure, but if you just run this, we have the network, and again the red nodes are the meetings and the blue nodes are the actors, and this is the two-mode network, of course. And then we can again make use of our projection. I'm gonna use the weighted projection, and I'm gonna remove the nodes from the projection, and I'm gonna copy again just a simple drawing, and we have this thing here. Okay, so this is the one-mode project network connecting actors that participating in the same meeting. Okay, but then we can make it in a bit nicer, right? And for making this a bit nicer, I'm going to extract the communities of this this network, so we can color the nodes by community. And I'm just going to extract the between and centrality, so we can just label some of them and see those people. Okay, for the community, I'm going to import this thing. I'm going to import the community package, and I'm going to use this script. So what I'm just doing here, okay, I forgot to fix this. What I'm doing here is just like I'm getting each actor to which community it belongs. Then I'm checking how many communities we have, and then I'm just reorganize the data and say, okay, in community 0 we have all these members, community 1 we have all these members, and so on. Okay, and then I'm gonna also extract the between the centrality, and the between the centrality. So the between the centrality it's equals to nx between the centrality of GW. I'm gonna have normalize true and normalize true with weights. There we go. And then we can just use a similar thing that we did before for the degrees to check who are those with highest between the centrality. And just let me correct this again. Collections. Okay, so let's import collections. or instead of importing collections, I already imported the counter from collections, right? So that should work. Okay. All right, so here we see those people with highest between centrality, for example. And then let's just create a more advanced drawing. So for this more advanced drawing, I'm gonna again just copy and what I'm doing is okay, the figure again, the environment, and I'm using a spring layout with more parameters this time, so I can we can just tweak those parameters and try to make a nicer figure. The colors, so the colors are just chosen manually based on the communities. So we saw that we have 6 communities, so I just give the colors, and actually I give one more here. The labeling, we're just gonna label those nodes with between centrality higher than 0.05, right? So drawing the nodes, drawing the edges with some parameters again to try to make it nicer, drawing the labels, and here are also added 2 lines here just to show you how to save those. Like here, for example, I'm saving a PNG file and a PDF file. I'm just we'll comment this out because we don't need that. And then if we just run this, we will have a nicer figure. Of course, we can change the size of the nodes like proportionally. For example, here I'm multiplying by 1.2. So if I just multiply, for example, by 2, no, I'm exponentiating actually. So if I just exponentiate by 1.5, 2 would be too much. We see like the nodes will be too much, too big actually. So it's just like tweaking the parameters so we can get nicer figures. Okay. So all right, so with this we reached the end of our workshop. It was really fast because of course we don't have much time. It would be much better if we could do this in presence, face to face. Hopefully we will be able to do this in the next years. And yeah, I hope you enjoyed, and let's take some more questions.